Hi, this is Professor Fernandez. We are doing class note C in lesson 5. And this class notes is really about proving this theorem 5.2.2. So let's first read the theorem and then we'll talk about what the proof looks like. So the theorem says if y of t equals u plus iv is a complex valued solution, so meaning that the solution involves complex numbers, of a homogeneous CC solved, that one, then y1 equals u of t and y2 equals u of t are two real valid solutions. Okay, great. So I just read the theorem. Let me boil down to what the takeaway is. So the takeaway is that if you are solving a CC solved and you get a complex valued solution, then the real part and the imaginary part are each solutions. So that's very good. Very nice, because when you start off solving a CC solved like this one, there are no complex numbers in here. So if you get a solution that involves a complex number, you might be wondering, how can I get rid of the pesky little I, right? It didn't show up initially, why should it be there at the end? And this theorem helps you do that. It tells you, well, if you get one of these complex valued solutions, just take the real part, take the imaginary part, and those two individually are solutions. And they're real because you got rid of the i's. So that's a very nice result. And the proof is actually fairly straightforward. So I've written it down here so we can just talk through it. So what's the proof? The first thing you want to do is you want to say, well, since y of t is a solution to this, that literally means that when you substitute it in for y, it satisfies the equation. Great, so that's what that means. And then from here on, it's just a matter of simplifying this to sort of extract the result. So what I'm going to do here is I'm going to combine everything that does not have an I. Okay, and that yields this little part. And then I'm going to go back and combine everything that does have an I. So this is, this times A gives me that part. This is this times B gives me that part. And this times C gives me that part. So this is the part that all multiplies I. And that's still equal to 0. And this is the part where you might think is a little sneaky, but I will scroll up to remind you why it's not sneaky. The right-hand side is 0, but that's when you view 0 as a real number. You can also view 0 as a complex number by writing it as 0 plus 0i. Right? That is totally true. 0 viewed as a real number is 0 because real numbers don't have imaginary parts. 0 viewed as a complex number is 0 plus 0i because complex numbers have a real part and an imaginary part. Okay, so this little fact is useful because now we are going to go back. I'll scroll up here to the definition that we have put in of complex numbers to begin with. Very, very start of this lesson. Here we are. And there's one little part that I made sure to put in here just to, pretty much for this very purpose of this proof of the theorem. We say that two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. Okay, great. So let's scroll down to where we were down here in this proof. And here we are. So we have, let me put them in the same color. Well, to the extent that I can, we have an equality of two complex numbers here. And we just said that two complex numbers are equal when their real parts are equal and when their imaginary parts are equal. Okay, so setting the real part equal to the real part on the right-hand side yields this. Setting the imaginary parts equal to each other yields this. And this is what it means for U to solve the CC solved. And this is what it means for V to solve the CC solved. Right? And that's exactly the conclusion of the theorem up here.